we're basically given that a model rocket is fired from the roof of an 80-foot tall building, and the height of the rocket is given by this equation. This is the height, y of t. I prefer to call it h of t, but that's fine. And then it tells me y0 is equal to 80, so I get 80 feet is the initial height of the rocket, v sub 0, so plus 120 feet per second. So there's no conversions needed yet, times t. So this is in feet. If I multiply this by seconds, it'll be in feet. And if I multiply this by seconds squared, it'll be in feet, which is probably, yeah, t squared. And then I have minus 1/2 times g, that's gravity, 32.2 feet per second squared times t squared. So everything now is in feet, which is good because we're trying to, this is supposedly the height of the rocket, so it should be in distance units. We wrote the quadratic equation for the height. We could also write it in standard form by just reversing everything, but I'll leave it like that for now. B, the velocity, which it's telling me is equal to the derivative of y of t. The derivative of y of t with respect to t, that's what that is saying, is equal to, well, the derivative of a constant is 0. I don't have to worry about that. The derivative of 120t is 120 times the derivative of t, which we already talked about. The derivative of x is 1, the derivative of t is also 1, minus 1/2 of 32.2 is 16.1. And then we're going to take the derivative of t squared, which is times 2t. So this is going to equal 120 minus 32.2 t. And now this is going to be in feet per second. And to tell me at a certain time, it does not tell me any particular time yet. I know now this is v of t, which is equal to 120 minus 32.2 t feet per second. This is feet. All right, let's do C. We want to find the derivative of the derivative. It's the second derivative. This is how you write the second derivative with these exponents on the d's. This is, so it's the second derivative of the position, the derivative of the velocity, and that's a of t. So a of t is equal to, we can also say v prime of t, which is the derivative of this. We have a constant, which goes to 0. We have minus 32.2t. Well, we pull out the constant. We take the derivative of t, which is 1. We don't have any variables left. And our acceleration is negative 32.2 feet per second squared. Here's my a of t. Here's my v of t. And we already found our y of t, which is our height. Well, now all we want to do is sketch the graph. First, I want to find the time required to reach the maximum height, as well as the corresponding height y max. Okay, what we haven't really talked about yet is the maximum height. Let's just think about this for a second. Let's say we have this graph and we hopefully know that it's a parabola. I don't know exactly where it's going to be, but I know that since it's negative as my first term, if I were to rewrite this, actually, let me rewrite this as y of t is equal to negative 16.1 t squared plus 120t plus 80. Now we can see that it's a parabola facing down. I don't know much more about anything. I don't know where it hits. I don't know. I have no idea. All I know is it's opening down, and I know this is its maximum height. I don't know what time it happens. I don't know anything else, right? But here's what I do know. If I were to draw a tangent line to that maximum point, it would look like this. It would be horizontal. And we know that the slope of a horizontal line is 0. If I were to take the derivative of this, because the derivative gives me the slope of the tangent line, which I semi-graphed, and I want to find that maximum point, we can say that it's when y prime of t, which is actually the same as v of t, is equal to 0. And if you think about what the velocity means, like imagine you throw a ball up in the air and it's going up because it has still some velocity from the initial throw. If you didn't put any initial velocity on it, it would just fall straight down to the ground, right? So it's going up because you threw it up with some velocity. When it starts running out because of gravity pushing down on it, at the very top, the velocity will be 0. And then when it starts coming down, we call that a negative velocity. At the very top, our velocity should be 0. And so that's why we take the first derivative and set it equal to 0, which is what we're going to do now. Well, we already took the first derivative, so all we have to do is say 0 equals 120 minus 32.2t. It's going to be 120 over 32.2, which is equal to 3.73. 3.73 seconds. And then what we want to do is plug this value into my original y of t. And we're going to square this plus 120 times 120 over 32.2 plus 80. All right. So we have negative 16.1 times 120 divided by 32.2. Nope. Squared plus 120 times 120 divided by 32.2 plus 80. And this is my answer right here. So 303.6. My maximum height is 303.6 feet. Max height when t equals 3.73 seconds. And that is, I believe, the solution to D. Let me just reread it. I think it wants me to graph it as well. Yeah. We'll sketch this graph. When I say sketch a graph, I mean sketch a graph. What do we know? Well, we know that if this is my original function, when t equals 0, it's going to be at 80 feet high. My y-intercept is here at 80. And then at, let's call this 3 seconds, and we'll call this 4 seconds. So we'll call this 3.73 seconds. And we know at that point, I know this is not to scale, but too bad. This is 303.6 feet. Here, let's say it's 100, 200, and then 300. That means I start here. I start somewhere around here at 80 feet. Here it's 300, so I'm coming up. That point is my highest, and then I'm going to come back down. Obviously, I'm not going to go below the ground. That's the end. The rocket's not going to hopefully go into the ground. So that should be the lowest point right there.